Something weird's going on with my setup.
separate, then why don't you put all the synapses on one
Sorry.
segment?
Yeah.
This is about active dendrites.
So let's talk about the first one first. There was a need, this is from my perspective, and other people may think differently about it, but there was a need, these are predictive models, and you had to make predictions. The models have to predict something. And the predictions can't be the same as the activations from the input. The predictions are not the same as input. And so when we thought about the cortex and where and predictions are ubiquitous, where are they occurring? And you kind of have two options. You could have like a set of neurons that are representing predictions and another set of neurons representing actual input. That may be the obvious thing, but it didn't seem that was the way. So from my perspective, when I first started thinking about it, I was asking the question, where are these ubiquitous predictions occurring in the cortex? And one of the reasons you have separate integration zones is that on the basal dendrites, you don't want to have the cell fire, you just want to have the cell polarize. It's a prediction. So even if you could put all the synapses on one dendritic zone, you don't want them all to fire the neuron. That doesn't serve the purpose. Mm-hmm. And similarly, there's a separate functional need for apical dendrites. There's a separate integration zone. So the reason you don't, one reason you don't combine them all is because they're representing different functions of the neuron. That's a pretty essential thing. And our neuron paper essentially said 90% of the synapses on a neuron are not making the cell fire.
Right.
And they're representing the model of the world, but they're representing the sort of predictions of the model of the world. So kind of like you can't throw that away.
I think that's probably the single biggest reason.
Yeah. That's where it came about, by the way. We were asking, how it is it the brain can make predictions of the next note in a melody, for example? Multiple predictions at the same time. Where are those predictions occurring? And how do you know when the predictions are met or not met? All these things had to be resolved. And so the big insight was, oh my God, every neuron is making predictions, every parental cell.
Yeah. I guess a little bit is also just the flabbergasting amount of synapses that are, just doing, very small subthresholds PSPs.
Yeah, there was no theory for what they're doing.
Why are there so many thousands and thousands of weak synapses on every neuron?
So think of this, more than 90% of the synapses on parental cells and spiny stellar cells are incapable of making the cell fire. More than 90%. So what is that? What are they doing?
Okay.
So
to me, like as somebody who always thinks a bit more from the anatomical side, although I appreciate the functional one, that is like the glaring thing.
Well,
you need some explanation.
Yeah, well, we need an explanation.
That was the title of our paper.
Yeah, right, of course. Yeah.
You need an explanation for it. You just can't make up one out of a block. You need something functional that really has to happen. So, so it's the merging of those two. There's observation, like you got to be joking that people thought that these synapses aren't really doing much. They're doing some sort of modulatory thing, which is right, but that doesn't tell you anything. And then the idea there has to be something fundamental to the brain that's being done by those things, and the answer is prediction.
Yeah, so I guess from a computational and functional standpoint, it's just that the set of operations done on these dendritic segments is different than what's done in the feed-forward segment. So you can't just have them all in one.
Yeah.
The actual computation is different. It has a different impact on the cell.
Well, not all.
That's the same thing as what.
So you're saying not all on one integration zone?
Well,
So that means you need at least two.
There's a separate
Yes,
question.
yes. There's a separate question of separate
Yeah.
compartments.
So
Yeah,
can we
yeah.
switch to the
So this means you need at least two things.
Yeah.
integration.
Yeah.
Okay.
Now, the next question is, why can't you put all the synapses together?
Yeah.
So it turns out you can what we call mix and match them. You can take, like, if I have a dendritic segment, I want to recognize a pattern. I can establish 20 synapses on that and recognize the pattern. Turns out you can stick another 20 synapses on that same, right? And mix and match them. They don't have to be physically segregated. And the math works out that those two sets of synapses, although potentially there's an error there, but you could get 10 from one pattern, 10 from the other pattern. Statistically, it's not going to happen. And you can do this up to a point.
Okay.
Now, there's two limits here. One is the size of the integration, physically, the size of the integration zone on the neuron is about 40 microns on the dendrite. So you can only get about 40 synapses or so in a, so you can't fit 200 patterns in an integration zone on a dendrite. I suppose you could in a point neuron, you just add them all together.
Yeah.
That's partly it.
But more importantly is, after you do this a bunch of times, as you keep adding more and more of these patterns together, so let's say I added 20 synapses for this pattern, 20 synapses for that pattern, at some point you start, the chance of errors actually goes up and it becomes significant. So it's trivial for 2 or 3, you won't get any problems, you won't have any mixing, you won't have any errors. But we did the numbers on this, we did simulations, I don't remember what we came up with, but at some point it got to be a problem. So you can't just mix 100.
So you can just add, units essentially in this representation to, if you just extend, I would like to understand if the number of units that you need to add in a single representation is somehow linear to the number of patterns that you want to recognize. I understand the biological, constraints of this, but just mathematically, it's just that you want to grow essentially the number of total, synapses, or it's
so there's
another module.
Two things you need in order to be able to what we call doing these unions. So a union would be you have 2 of these patterns instead of 1 together. You take the OR of them. You can still have that each.
Are we talking about the union of activations, or are we talking about the union of synapses?
The union of synapses.
Okay.
Yeah. So you can have more and more of these, and the question is, what are the key dimensions or key parameters that say how accurately you can do this, or how much you can do it? Right? And there's 2 basic things that impact how many you can do. One is the underlying dimensionality of the representation.
Okay.
So if you have 100-dimensional representation and you're sticking 20 synapses at a time, you can only do maybe a couple of them before you have a problem. But if you have 10,000-dimensional representation and you're sticking 20 at a time, you can do a lot of them before you start getting into this mixed dimension. So the dimensionality of the representation, independent of the number of synapses, is really important.
Yeah.
And then the second is just having really sparse representations. So you want a relatively small number, very small percentage of that dimensionality for each pattern. Those are the 2 factors that impact how many unions you can do.
Before you start.
But technically, so it's a matter of efficiency. In a sense, you could theoretically, increase the dimensions of the representations of the synapses.
If you want to have, a million neurons and say only, 40 are active in any particular representation, and you're going to connect to 20 of them, well, then sure, you can get a hell of a lot of unions that before you start interacting. But there's downsides to that. The biological part is downsides. You can't do that.
And there would be in a machine learning system too. You would have, if you had 1 million units in a layer, that's a lot more expensive.
Yeah,
than
of the big vectors.
Yeah.
And corresponding matrices also.
So Simon did this nice analysis, which is in the little box in the neuron paper, why neurons have thousands of synapses. And he did this simulation, I hope I get this right, where there's a lot of parameters here, and not the parameters in neural networks. And so he did a bunch of simulations of sort of realistic ranges of things. And he could sort of summarize the results in a nice way and show that in some ways what nature has settled on for these numbers seems to be sort of right in the sweet spot of all these possible scenarios. And it's not proof or anything, but it's a very, very nice result. And so, why did the synapses, why do we see, integration zones of, why do dendritic spikes occur somewhere between like 15 and 20, active synapses? Mathematically, and simulation-wise, it just comes out that's about an ideal scenario. From meeting all the different requirements, the number of units and the sparsity and so on. Another thing in the brain, again, we don't have to stick to this in our other stuff, but in the brain, there's a challenge for neurons to make connections to other neurons, and so the whole idea of a potential synapse, neurons have to be close enough to each other that you can form these synapses. In software, we can do whatever we want, but physically in the brain, there's restrictions.
Yeah.
So so that we don't always have to adhere to the way the numbers the brain has. It's a good place to start.
Like the way you see these when they draw the synapses is always as if there was nothing around them, like empty space. And in fact, many of these staining techniques, they work well because they don't actually stain every neuron. They stain every 1,000th neuron. And then when you do that, then it actually looks really nice. And it looks like they have these nice, beautiful arbors. But of course, in reality, it's a packed tissue. There is no free space, right? There's no empty holes between the neurons. It's all packed with dendrites and axons and glial cells and, fibers that pass through and whatnot. So that's important to keep in mind. It's really a spatial struggle in the brain.
If you've ever seen these reconstructions that you're doing now, even something as small as a 10th by 10th of a millimeter cubic, 10th by 10th by 10th, the amount of stuff in there is just unbelievable. It's as if you took, piles of spaghetti and fruit and stuff, and you put it into a big compactor and you smushed it all together, and it's just like a mess. There's no space.
Right.
So, how many axons go near dendrites? It's really complicated, and they're just wiggling all over the place, every which way.
They do this thing where they slice the cortical sheet with micrometer thin slices, and then they use computer vision technology to try to track, if there's an axon going through the sheet, right? So you have all these slices, and you try to track, how it goes and where it branches, and to build these recreations, right?
But none of that matters from your question is. So I think that's the.
Yeah, maybe I can summarize by building up the neuron model again.
Turn the light on.
And then just repeating what we've already said, and then maybe I'll add one more point.
Of course.
So here's a neuron. Yeah. So one.
That's interesting, isn't it? Machine learning people don't draw this triangle.
Right.
But there was like these
We're doing this all with internal neurons.
This is more like a pyramid. Yeah.
I never noticed that before.
So the first question was, and I'm not going to draw arrows coming into it. It's, the first question is, well, why not just have only one dendrite, one thing? Okay, so one answer there that Jeff said is that you need at least a second dendrite because these ones will do prediction, and these ones will do activations. And this one has an impact on time t+1, and this one has an impact right on time t. All right, so the function of this on the cell is quite different than the function of this. So just for that, you need at least two. And then you can ask, okay, so this is detecting some patterns that form the prediction. Why don't you just put all the patterns here that cause a prediction and treat that as a union things. And so there, with unions, you get capacity limitations.
You know what you mean by union, right? You're following that, that we're just mixing those together.
Yeah, mix and match. And the same thing goes here for any dendrite. And this is just a mathematical property. You can just describe it very clearly mathematically, and we can do that at some point if you want.
It's interesting to me that you use the word unions in this situation. I would think of this more as pooling on that one dendrite.
But pooling to me is a type of union.
I mean, the thing is, of course,
because we're not talking about unions. We're not talking about multiple patterns active at a time. We're talking about growing synapses to multiple patterns, which is usually what we call pooling. But
but I think of this as pooling. The limitations of pooling. To me, pooling the function here is a subset of unions. Is that there's other things that go along with pooling, like stability and being on for a long period of time potentially. But this is, to me, this is math. To the answer.
You're thinking mathematically, it's a union.
It's a union, yeah.
And you're thinking sort of functionally, it's more pooling.
Yeah, and I think that's both correct. It's just, I think to answer his question, it's really a union limitation issue, and you can quantify this exactly. So because of that, because you can't put too many patterns, we end up having lots of dendrites, and because each one can recognize a couple of patterns, one or more patterns, and they can be completely segregated. You run it to the union limitation. And so you can do hundreds of patterns, contextual patterns. So that's the second benefit, this capacity thing. And I think there's a third one, which is a learning benefit. So if you recognize a pattern and it's either correct or incorrect, you want to update just the synapses for that pattern. If everything was all union together, even if it was within the capacity, it'd be really hard to update just that pattern, because there's no real knowledge of it anymore. What is that pattern? But if it's segregated like this, you could do branch-specific learning on these things so that you update the synapses or weights only for that pattern. And I think that makes learning much more efficient. And so,
absolutely.
would you agree with
Yeah,
that?
I agree.
So that's, I think, a third benefit.
I'm tempted to go give a more biologically accurate picture of this, but.
Yeah, but I'm just sort of answering from an abstract machine learning point of view, ignoring biological considerations for a second. But this is obviously, all these inspirations come from the biology, but this is completely checked. And then from a continuous learning standpoint, we know that if you have very sparse representations, that the chance of a single pattern activating falsely some of these other ones is very small. So now you can learn new things on new dendritic segments without any interference with the old ones.
Yeah, that I understand. But so my idea was, if we have just one active dendrite, and then we have more of these entire neuron model.
Oh yeah,
and it's sparse. So essentially, you're doing the same thing.
That's right. Yeah.
You have the same properties.
Yeah, exactly. Yeah, so that's true. That's true. So in our temporal memory, we have.
You say you can trade off multiple dendritic segments for higher.
More neurons.
Yeah.
And
that's
that's
back to the question I was asking.
Yeah, that's totally true. So you could have, in our temporal memory, we have multiple cells per column. Each one has, let's say, 3 different active dendrites. Well, you could have 3 times as many cells with 1 active dendrite each, and that would be fine. It's just now it gets a question of resources and computational efficiency.
So we mentioned that Florian talked about his model a little while ago, and he said he had like 32 neurons in a column. We started with that number 2, because that's sort of the maximum you might see in a layer 3 or 4, something like that. It's probably less than that, but you're not going to find 100 neurons in that column in layer 3. It's not going to happen. So again, we were trying to match the biology more, and so the biology gives you good suggestions, and if you follow the biology, then you kind of learn good rules, and there's usually a good reason the biology ended up that way. So at least you should know that before you go away from that.
I got a question in that context. So we have multiple dendritic branches, and I buy that just from the biological fact that there's clearly identifiable branches anatomically. And I think it's helpful to think of that as spatial pooling, in the sense that it's actually pooling inputs from like different directions from the neuron, like so sort of laterally, right? Since they're growing out away from the soma. And they're growing out in different directions.
Well, I don't know if the directions matter as much in the cloud around the neuron.
Right, you see, that's what I'm wondering at. That's actually my question. So whether for the model, it would be helpful to have an understanding that it is actually spatially divergent, that it's a tree that's branching out. And I don't mean to introduce multiple levels on the dendrite, that's not what I mean. But what I mean is that while we draw them here in parallel, which kind of would suggest that you could have like a descending fiber that would activate all of them. No. In practice, right? Of course, these are branched out in different directions. Yeah. And that means that they in fact pool different fibers.
Well, maybe because those fibers are going all over the place. I mean, we could draw the axon of some cell going vertically.
Right.
But usually get to the end of the axon, it's like,
But right now, one way I like to think of this question is that you want your potential pool to be as large as possible of the cells that you could connect to, and because you have physical limitations, if you have them going all over the place, you can potentially connect to many more axons than if they were all like in one.
Right, but I'm not
Is
sure
that-
that's
is that-
true, because if you actually had a spatial model, wouldn't that reduce potential interference? Wouldn't it increase the likelihood that the different patterns are actually recognized on different branches?
What is that?
Because
You're-
there's spatial structure in the pool.
Yeah,
So it's
you're
not random on which
you're
branch.
arguing.
Yeah, but
that-
there's not, I don't think you have such fine spatial structure in the level of microns here.
Right.
That's at the level of, many columns you have, but within the
Right.
context of a
I
cell,
mean, yeah.
I think,
I mean, you're just talking about this spatial, you're trying to say, is this spatial arrangement here, actually, is that important?
Yeah.
and even like
I-
this versus this, but I don't, this,
Maybe.
this-
Well, at least
it's not that, I
It's
don't think
not-
the spatial
I-
structure
I,
is
you
that
know,
fine.
a typical pyramidal neuron, the diameter of this cloud it looks big compared to the cell body, but it's not very big overall. I'm trying to think about, it can be maybe, I'm tempted to put a number, I'm not sure, maybe 0.5 millimeter or something like that.
Right.
Um,
I don't buy that.
And within that kind of range, everything is going squiggly wiggly all over the place, and so I'm not sure you're going to take advantage of it. But it's an interesting question. It's an interesting question. We haven't taken advantage of
But
it.
you just like equally distributed random connections, right?
Right.
And then you rely on coincident activation, which is fine, right? It works.
Yeah.
I'm just wondering if the problem of interference couldn't be helped, right? The fact that it would be helpful to actually have some structure in it.
We haven't had much problem with interference at all. It really is just not, it's never really been a big issue. Only gets when we train like the sequence memory, and we trained it until it started to fail. And you had a gazillion synapses out there. It wasn't like even close to being a critical parameter. I think it's worth pointing out a couple of distinctions here. This is a biological distinction, and may not be important from any other point of view. Just to reiterate, there are no excitatory synapses on the cell body. None. Right? There are inhibitory synapses in the cell body. So unlike a point neuron in a neural network or so, they're all being summed at the cell body. That's not going to happen here. There's basically within some distance of the cell body, the proximal synapses, they are close enough that they act as if they're summing at the cell body. And so there can be, depending how many basic branches coming off the soma, there's some number of synapses here, and that typically, those represent less than 10% of the cell, the synapses on the cell. On a V1 neuron, it might be 5 to 7% of those synapses. Those are the ones your classic sum spike. Then, of course, all the others are further away, and I'm actually not sure how distant it is till you get to your first branch point. I don't know if there's some here that don't qualify as proximal, but clearly after the first branch point, the synapses are all too far away these are all these sort of prediction synapses. The other thing I want to point out is that these branches on a real neuron, the length of one of these terminal branches here can be 200 microns. And that's a lot longer than the integration zone of 40 microns. So with that idea, the integration zone is you have to have some number of, within 40 microns of distance, you have to have some number of synapses, 15 to 25 or something like that, that are active within some very short period of time, that they integrate together and produce a dendritic spike. If you stretch those out over 200 microns, it wouldn't work. So already what that tells you is it's not as simple as we draw it here. We just keep adding segments. Why not? In the real neuron, you might argue there might be 10 in here, 20 synapses for each. So we don't really, again, none of that seems to matter at the moment. And even the thing that Subutai was pointing out is if I'm going to mix and match them on here on this 200 microns, they're not going to be mixed and matched over the whole distance because that's more than 40 microns. So on that 200 microns, you're going to have some pattern recognized on 40 here, and another pattern recognized maybe on 40 here, that kind of thing. So, the pattern over here and the pattern over here are not really combined together. They're not really competing with one another. And somehow the learning signal comes back. We don't know if it affects all these synapses or if there's still a local effect from this little area that was depolarized and generated. It's possible that this generated the dendritic spike and that there's a local effect there, a metabolic effect or something that this gets trained on. We don't really know that. But anyway, I just want to point out that these dendrites, The terminal dendrites tend to be long. And the other thing that, going back to what Florian mentioned ago, it's related to it, the tips of these dendrites are constantly growing and retracting. It's as if they're just trying to find something. You know, like, oh, no, I'm in this direction for a minute, see if I make a connection. Oh, no, I didn't. But if they do make a connection, if they find some synapses that are useful, then they stop, you know, hey, I'll keep that segment. And I don't know why, you know, I guess presumably they don't keep growing forever because they can't keep finding things to connect to. I don't know.
Also, maybe just the signaling efficacy goes down.
Or maybe, yes, it gets too far away. The back action potential and the forward, yes, there might be a physical limit to the distance here. But they do seem to very actively all the time just sort of growing it out and trying, growing this way and trying. They're all trying to form new connections all the time. Yeah, so it's a little bit in between this idealized thing, but this is a good way of approximating that. We didn't really need to model it this way. And there are evidence, by the way, there's evidence, some people argue that there's additional type of learning that's occurring at the branches of the dendrites. And so there's a whole little subfield of people who study that. And we haven't, I don't know if it's true, and we haven't incorporated that in any of our models.
So you mean at the junction point?
Yeah, some people argue that these junction points, I think people argue everything, right? I mean, but these are very non-linear points here that all of a sudden, you know, the whole sort of modeling property of the dendritic segment falls apart here. Because you've got this, the whole, the cable, as they call the cable properties of the dendrites. When you get this junction, it all kind of gets messed up. The capacitance and the current flow, it's just, you know, you can't model it very easily anymore. So there's a group of people who think there's something really important happening at these things. There's some kind of learning that's occurring there. That may be true. I don't know. But anyway, I just wanted to put this more of the reality of what a real learning looks like. But I think our model is pretty good. And we don't, and we did, and it turns out that the apical dendrites, the one that are at the tall top of that, go up top, they seem to have they have different properties, and they would form a slightly different type of function. And we did model that in terms of our pooling. I think we did. We did with it.
A little bit.
Feedback.
Yeah.
But I don't think we did it really correctly.
No, so we're not capturing everything that's going on there, but just to be clear, as far as I know, we're the only people with any kind of functional model that explains what the hell all the dendrites are doing.
There are other people who are building some morphologically detailed models and try to put them in a bigger context, like the V1 model that we were looking at in the course of the what's it, Yassan Bile, with this big thing at the Alan Rain Institute, but they are not. They still sort of argue that there's sort of that you can approximate all these synapses with one number for the EPSP and PSP, so it's still sort of like a static strength kind of a thing. They don't really differentiate. Like the model might then actually make a difference depending on the fact that like these synapses are going to be more effective at integrating information because they're closer to the cell body when you build a morphological model, but they're not really accounting for much of the nonlinearities that occur at these dendritic branching points. The fact that you might get sort of like a summing junction that could act as a prediction filter, right? The way that they use it. So in that sense, it's kind of fascinating how Numenta, even though it's like more machine learning oriented, is actually capturing more biological detail in some aspects, right? While obviously abstracting it very far with, you know, sort of like idealized, you know, like segments and the random connection probability. So not bothering with all the biophysical modeling with the spatial structure, right? In that sense, you know.
It makes total sense. I mean, if you think it's you know, the brain has a huge capacity for knowledge, right? We just an incredible number of things. And in the end, you have to take advantage of all these synapses to store all that knowledge. And so it doesn't, I mean, it's almost like it just begs out that there can't be inefficiencies in the system. It has to, and so the idea that these different segments are learning different things, just in the end, it just almost feels like it has to be that way. And so anything that just sort of gloms it all together and sort of mushes it into some sort of, something else, it just seems that neurons have to be far more precise in their knowledge than most people think. And that's what we're arguing, basically, is in the neuron knows all these unique patterns, and it's all these different contexts in which it can make predictions. So it's from that point of view, it's very satisfying. But I don't know if everyone sees it that way.
It's also important to point out that like synapses are expensive, like in terms of like the biomolecular machinery needed to build them, to maintain them, to do things like
I heard it is like some
reuptake.
metabolic analysis on that, and I thought it was like, I can't remember what it was, but it was surprisingly high.
Yeah, there's
The energy in the brain that's maintaining
Yeah.
synapses, it's always like the large
Right.
portion of the energy.
so like 30 to 40% is just maintaining all the voltage gradients and so the actual spiking potentials, and then you have some 30-40% energy use for the entire machinery, so not the ion gradients, but all the transmitter gradients, so like the reuptake and the building of the vesicles and the releasing of the vesicles,
Yeah.
all that machinery. And then there's some 20% on top for much of the plasticity machinery. So that roughly sums to the 100%.
What about spiking itself? That should take up.
Yeah, that's like the 30%. That's included in the 35% of the like voltage gradients. That was like I did a review on that with a colleague of mine because we were wondering, if we could, like argue about why do we need spiking models, and how do they?
So 70% can be about learning somehow.
Yeah, it depends on how you group things, right? Because of course you need all of it to do learning.
I think the point of maintaining these dendritic trees is really expensive, right? It's the bulk of the volume of the brain is dendrites and synapses, and really it's the bulk of the volume of the brain.
Like, to understand that how complex this machinery is, it's worthwhile to sort of revisit evolution. Like how many different proteins do you find at a synapse? And if you look at sort of the earliest forms of life that have some kind of nervous system, you might find some 20-30 different proteins. At the human synapse, that is at its peak. There's like estimates range a little bit, but thousands of different proteins in the small confines of a synaptic neuron. And if you like combine pre and postsynaptic sites, you get to several thousand of like different proteins.
Right.
And they all do different. This is like highly specialized machinery. It exploded over the course of evolution. And so these are the most complex small machineries that we have. I mean, there's lots of complicated machinations in the whole body, but nowhere is it as dense.
Is very complex.
There's no more dense, complex.
You can also look at it
machinery
similar. I
as the
thought you were
synapse.
going to make a similar argument that if you look at the neurons in simple animals, like Campbell studied the Plesius snail, right? And the old neurons and the old parts of the brain and so on, and these simple animals, they didn't have these thousands of synapses like this. The synapses were, one of the things about Plesius is that every synapse is the same in every animal, so they were genetically determined. And so, there were maybe a couple hundred synapses on a neuron, and they were there, and they're always there, and every animal has them. And this idea, all of a sudden, you have these tens of thousands of synapses on neurons, and they're coming and going, is a more recent invention, evolution-wise as well. So it went from being sort of a control, engineered controlling system to this learning system, where you have, and that's where all the knowledge of your world is in these synapses. So
you said this make their fix.
like they say, different animals of the Plesius species have the same synapses.
So
Also the exact same total number of neurons.
The exact same connections.
It's like exactly 160
This is neuron
neurons.
47-2 B, and every animal has the same neurons and the same synapses.
but I guess if I look at
Right?
monkey or like human brain, at least small percentage of that would be also fixed.
Well,
The older brain structures.
the older brain structures,
Yeah.
yeah.
Okay.
I'm not sure if it's fixed, I don't know if it ever, probably, it's certainly simpler.
Right.
It's more genetically determined.
I mean, some stuff is pretty bad, like the freaking knee reflex, right? There's literally like an inhibitory neuron in the back of your spine. It's always there, and it's if you're physiologically healthy, you don't have genetic defects, it's always going to work,
Yeah.
and it's just set up genetically. There's no learning involved.
No learning
right?
involved.
These are all old part of.
Yeah, well, it's
Yeah.
of course.
Yeah, the spinal cord is part of the brain in some ways.
Yeah, it is. It's considered, it's the first part of the brain that evolved. The simplest animals have the equivalent of a spinal cord. And then they didn't even have, there wasn't even one that wasn't different than the other. And then the next thing happened, you start to have a little bulb at the end of the spinal cord at one end. That's
These
sort of what-
additional things.
So that's where they have some centralized control for like heart rate or breathing or something like that.
Because you can do things like bipedal walk and or like multipedal walk, like in a 1,000-legged, insect. You can do this with like local computation on each segment, so you don't need a central system for that. So like certain forms of locomotions, like there's all these people who are studying these things. I have colleagues of mine who are building models of that. What is it? Like these water snakes. Forgot the name. But yeah, anyway, so it's all about like these pattern generators that then give rise to the locomotive abilities of like these early nervous systems.
So these properties you're talking about here are primarily properties of pyramidal cells. The argument, there's another type of cell called the spiny stellate cell, which is people have argued is like a pyramidal cell without the apical dendrite. They are really only in the more recent parts of the brain. So you'll see them also in the hippocampus and the antemorphic cortex, but they're 80% of the cells in the neocortex. And but if you go old brain structures, you don't see these cells there. You see other types of neurons that are presumably simpler. Anyway, that was one of your questions.
Yeah, the second part was about if we want to bring essentially some more complexity into the deep learning world. Especially in the context of continual learning, where the important part is to disentangle weights and representations. I'm still wondering if it is important to bring somehow the complexity of a more elaborated.
Well, that's why you asked the question, couldn't we just put this all in one?
Yeah, exactly.
So we've already answered this. There's two reasons again. One is because you have to separate functionally, and the second one is you mathematically have to separate them at some point.
Yeah.
So I don't see how you can get around that ultimately.
So the first idea is to just add more neurons.
Yeah. So a typical deep learning network does not have the concept of a predictive state.
Yeah, that's
So if you just want
from that, let's say that that could arise somehow naturally from a recurrent connection, right? Somehow we can think of the predictive state as as the state that is somehow kept inside the neuron with subsequent recurrent connection.
Yeah, something like that. Right.
Anyway,
Just to say, we're saying
let's say
you're going from the point neuron where. So what I do, I'm getting out of my realm of knowledge here. The way I view it is right now in these neurons and these neural networks, one of the reasons it's so hard to train is that you're always summing all the inputs to the neuron. And therefore, to get the neuron to respond differentially under different conditions, you have to very fine tune these weights based on the very specific activations of the individual input neuron.
Yeah, a lot of constraints.
You're trying to move all these things in this continuous space just to find the right combination to make sure that this cell fires on the one condition but doesn't fire on the other condition.
Yeah.
And that is a fundamentally difficult problem. I think that's the core reason you have to retrain these networks over and over and over again, because you have to sort of settle very slowly on the right
it's a
solution.
global optimization.
Yes, and you have to settle very slowly.
Whereas this kind of stuff, you could just do it locally and it's very fast.
So this seems a fundamental way of getting around the slow, difficult learning process in neural networks, is to compartmentalize the learning like this with sparsity and separate active,
Yeah, one difference between just adding recurrent connections and the way this works is that the recurrent connection should not be able to drive the cell. Right, it just acts as a modulatory impact.
Mm-hmm.
Right, so that's different from just pure recurrent connections in the typical deep learning scenario.
Yeah, just to make things simpler, we could just, just not work with sequence model problems.
Just do a static.
Static that's the predictive state of these cells. It's interesting when you want to model sequences, right? Most of all.
Well, you want to model anything more complex than that.
Yeah, exactly. Yeah, exactly.
Yeah, I think you could take, the way I thought of it, we're not going to do that first off, but you could get you could get a lot of benefits to the existing model by sparsifying everything.
Yeah, exactly. So
Sparsifying the activations, and then by having these dendritic segment equivalents, then all of a sudden you can do this continuous learning.
yeah.
So are you asking this, let me see if I'm understanding your question. So you could have, 10 neurons, each with 10 active dendrites.
Mhm.
This is a pure static case.
Yeah.
Or you could have 100 neurons, each with one dendrite,
So,
right?
Yeah, I want to ask you, if you think that, especially for a first step, in this direction, it is worth, getting rid of the idea of having multiple, dendrites and put a little more complexity into the deep learning world.
Yeah, so I think this will be computationally more efficient.
Yeah.
Than this, because you have these huge matrices between this and that.
Yeah.
So that's one answer, one possible thing that's important. The other thing is, I don't know there's a benefit. In theory, you could create more efficient representations here than you could here, because if multiple things essentially mean the same thing, you could group them here. Whereas it's difficult to do that here. You'd have to learn. And we talked about this a little bit before.
Yeah,
That's less clear to me whether that'll happen.
You do that in the upper layers. Let's say this pooling effect.
Yeah, but then you'd have to learn each one separately. Right here, let's say the upper layer, this means this has some particular meaning. The upper layer learns a weight to it. You could add new things here that mean the same thing, new patterns, and the upper layers don't have to learn anything new. Right? They already know that. So there's some efficiency, learning efficiency potential here.
Yeah.
I don't know if that will actually happen.
Would this may impact too, the idea that one of the nice things about this is that in some sense the network architecture stays the same, and when we learn, the way we learn now is we add new dendritic segments, but in theory, you're not adding new neurons, right?
Yeah.
And in the second scenario, if you want to add something new, you have to add new neurons.
Well, or you just have a really large set to begin with.
So what are all those neurons doing if they're not active at any point in time, right?
Yeah.
It seems like, I don't know, just a sort of a high level observation. The way we have it now, the way we model it now, you've got a fixed number of fixed resources. That was an important constraint on our models, because we know the brain doesn't add new neurons all the time. It does, but slowly. So you've got a certain amount of resources to work with, and you want to allocate that resources correctly. So this allows you to add, to do very rapid learning, creating new patterns that you can recognize without changing the fundamental architecture of the neurons. It seems to me that there's some advantage to that. I can't put my finger on it right now, but you could say, well, I'll just add more units in the bottom scenario there, but then everything else gets messed up. If you add more units here, then who's connecting to them and when? I don't know. It just seems like it's not going to work very well.
It's like the sparsity application that you're doing right now, right? You're doing right now. This idea that you have this, now it's sparsity level is 10% or something.
Yeah, we're getting lower now, but yeah.
So the concept that you don't use all the neurons at the same time, right?
Yeah.
I have an idea. So essentially, what I've been thinking about, and what sort of just clicked in my head, what is interesting about these dendrites is exactly that they don't make it necessary for the learning to go down all the way. It doesn't need to suffice the whole network criteria. It doesn't need to be retrained on the whole data set, whatnot. If you wanted to marry that to deep learning network architectures, right? So I recognize the first step for us is like sparsity here, but if you wanted to talk about active dendrites, I think what that would translate to is a switched backpropagation. So you will still, like, if you had a mixed system, right? Where you would use multiple dendrite neurons, but you wanted to learn them as a convolutional neural network with, traditional gradient descent. Then what that would mean in practice is that the error does not propagate all the way back, but in fact, it propagates only part of the way back, and there is an actual stopping condition depending on the dendritic activation. So you still can backpropagate the error, but only if the dendritic segment actually took part, and if it didn't take part, you stop propagating the error backward. That makes training cheaper, and it allows exactly for this weird property that not every neuron takes part in sufficing the constraints of all the patterns to be trained.
I think to some extent that would actually just magically happen if you set up this network. When you set up like all the logic with maxing and minning and stuff, those gates already have all that magic built in to where if something gets maxed out, if something gets clamped, gradient stops right there. So I think that would be what someone would accidentally code, and you just provided a justification for it.
Right.
Yeah, the problem is that they are not sparse, so you don't have this property enforced so much. It's just if you consider normal activations, it's 60% of these neurons are active, so it's a large population that is active. At the same time, it is taking part of these global optimization problems. All the weights are important, so it's still.
So I understand.
They are not just too much.
Just think about the second step right after this first.
I mean, it's all about having disentangled parameters and representations as well. So of course, if you have a very sparse, system in terms of parameters and in terms of activations, you can work much better. But that was also another question. So if for you, for example, what do you think that sparsity is enough for continual learning? Maybe if we don't take advantage of the these multiple active dendrites, and we think that it's just about having more neurons that are sparse and produce sparse representations and are
fundamentally, the nice thing about the way we think these neurons work is that it can learn something new and it affects nothing about what it learned before. Zero.
Right.
Now, if you can keep that, great. If you do something that moves that, then you've lost something important.
Right. I think that's
yeah. I mean, the complexity is trying to have the perks and advantages of back propagation and solving the gradient assignment problem along to get these hierarchical meaningful representations, and at the same time be efficient and having these compartmentalized
It's an interesting question. I mean, right now, correct me if I'm wrong, but right now I think what we're doing here, because I'm not really involved in it intimately, is we're trying to stick to the backprop neural networks architectures and add sparsity without changing any of the fundamental ideas behind them.
Yeah.
The question you're asking, I think, is if we now go to a sort of a segmented multi-compartmental neuron, can you do that still under the complete context of backpropagation and everything else?
Yeah, that's.
Or do you have to, or do you have to abandon that component and come up with a different learning rule? Is that what you're asking?
Well, first of all, if there is an advantage in doing so, is there a functional advantage?
Well, we know there's a functional advantage of
in these
models. And since neural networks today don't do this fast learning, and so there seems to be, there's a problem to be solved, and we know how the brain solves it. I mean, maybe there's another solution to it, I don't know. But so that seems like a good place to start from, right? So the only question is, how do we merge these two, right? Like and I don't know the answer to that. It would be nice if we could add all this and maintain the backprop learning rule that people are used to today, but maybe they have to be modified. I don't know. Is that, Mike, summarizing that correctly? Is that the question?
Yeah, and I think you can bring a lot of it over to the deep learning world, but figuring out exactly how much I don't know.
So the question is really, where does it break, right?
Yeah, well, we're already breaking a little bit by adding sparsity. We're already
Yeah,
sort of
sure.
breaking
Right.
things a little bit here and there. The question is, how much do we have to break more to add these compartmentalized neurons to get the benefit of the,
I think if we're clever, we can keep coming up with ways to bring things over for a while.
well, that's good. we generally express cleverness here every once in a while, so that's good.
Yeah, I think 3 years ago in December, there was a little bit of cleverness at some point.
We got lots of little moments. So,
I was just
For like 1 minute, what's this event?
Yeah.
So that's, I mean, I think that's the trick we're trying to see here, right? How much of this can we do before we have to tell people, by the way, you know, we really have to make a big leap.
So, yeah, so if you're really thinking without any temporal sequences, just static thing, you know, what is the difference between these two? I think there's at least a computational efficiency, and there may be a learning efficiency.
I think there's gonna be more than that. To me, it's my intuition, and it's purely just that intuition, is anytime you change, you add units to the network. If that's what you're gonna have to do here, or you have units that are not doing anything, now they're doing something, like, that's the same as adding, right? So what do you do with all those units? Are they computing
Wasted.
something?
They're just wasting.
But how do you know? Are they not active? Are they active meaningless active?
Well, that's something you'd have to solve. Like, how do you know when to train something?
To me, that is just gonna totally break things. I could be wrong about that, but the idea is all of a sudden you add these new units, so then we have units in the next level up, we're gonna have to know about that, all of a sudden which ones are gonna point to it.
Well, that's what I was saying here, that the next levels up, you can reuse the representation.
so-
That's the
So
distributed.
my intuition says that that's the bottom approach is just not gonna work well. Where the upper one is much more likely to work well. But I can't
I
prove.
mean, it'll work up to some point with simplistic scenarios,
Yeah,
but it's not
it
clear.
seems
It's,
like-
yeah. It's not-
We thought about a lot of models early on here, I did, I can't remember, but early on concluded you don't want to learn by adding new units. I reached this conclusion a long time ago. And maybe we did as a group, I don't remember. But that's just not a good way of going about it. It's just gonna lead to all kinds of problems. And so you've got to stick with what I used to call fixed resources or fixed, what was the term? I can't remember. Fixed resources. And you say, okay, that's the way the brain works. We got to do it that way. And adding more units is just going to mess things up.
I mean, there is neurogenesis in the brain. It does take a role for certain kinds of learning, but it's really rare and it's very specific edge cases.
Yes, exactly.
So it's not at all a universal principle of the brain to add units for learning
Yes.
at all.
Yeah.
You can say that very confidently.
I mean, you can see these. So your model, if you draw it like this, right? So these are active dendrites, right, that you have. But then you can.
So those aren't.
I'd say that you have.
Those are dendrites, and those aren't converging inputs, or.
I mean, in the.
But so each one of these will have multiple weights.
I
in
would
it.
draw the
Is that right?
active dendrites horizontally, so you're not confusing with like the inputs that.
Yeah, are these 3 inputs coming in or 3 separate segments, each of which has inputs coming in? What are you drawing there?
When you draw a point neuron like that, that means that neuron has 3 synapses.
Yeah,
That's not, but you said they're active dendrites, so.
Yeah, right.
It's more like, I don't know what you were gonna say, Vicente, but it's more like, here's our unit, and then over here, you've got this thing that has boom, boom, boom converting on it, and then there's another one that has boom, boom, boom converging on it, and another one that has boom, boom, boom converging on it. And so.
Yeah, absolutely. It's.
So I draw the dendrites
like-
horizontally, and I draw the converging.
It's like this. This is your model, right? So.
Oh, okay.
But these are
Oh, you want to see, these are the
okay.
active, these are the dendrite.
What I meant
see,
is that-
what you're saying. Yeah.
So this is an active.
Correct, yeah.
Okay. So essentially you can translate this in standard point
Yeah, okay.
neuron
Yeah.
if you don't take into account all this stuff about.
So here's
creative states.
well, that's right. So,
Yeah.
so here, you get this argument a lot, especially from people doing hardware.
Yeah.
They don't want to model neurons with dendrites. So they say, I don't want to do that. And they say, well, your neuron model here we could just model that as a set of point neurons. Here's a point neuron, 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 and a point neuron. Great, they say, we don't need to do this. But that is not true. It might be true for some simple, something, very simple thing, but the problem here is that the learning rules of these things are not the same as the learning rules for these things. And there's a communication has to occur between these that you don't have in normal point neurons, right? Because as we pointed out many times, when this guy fires, it's gonna basically cause a learning event in one of these guys.
Right. Yeah.
And because we're not going to learn in every one of these things, and so now there has to be these are not equal anymore, and so you basically have to say, oh, the new learning rule is that when this cell fires, we have to find out which of the neurons was inputting into it, and which one it caused that to fire, and then I want to train that one. Mm-hmm. And so that doesn't often. So I was at this neuromorphic hardware conference, the NICE conference, and this is when I met Karl-Heinz Meyer, and he spoke and I spoke. We were back to back, and he came up to me after my talk, after I presented this neuron model, and he said, everyone's been telling me I don't need to model compartmental neurons because they're just like this. And then he said to me after he saw my talk, now I realize that I can't do it that way. I have to do it this way because you can't take those point neuron models and make it behave like this one because of this odd communication.
No, of course, right.
Well,
in the complex part, in the complex,
in the
version of it,
particularly when you have prediction. Sequences, that gets hard.
But you could, I mean,
in a static case, that it would work okay.
Yeah, it'd be fine. But as soon as you start adding these unusual learning rules, well, then you're essentially modeling this. It's right.
In a static case, that would work fine because if this guy didn't fire, even in background, there's no learning.
Right?
Yeah, there's no updating that happens.
Yeah. So the fact that he was saying before.
So maybe it would work in this case.
In the static case, it's the temporal case that's different.
And another thing is that, I mean, coming back to this idea, it's just, it's just that structurally you're having a different neuron with instead of a different dendritic segment. But essentially it's all fixed. It's a structure, and then you learn.
But then you run into those issues we talked about.
Exactly.
But it's
so
still
I don't know if it's more
So
efficient one
this
way
is
or
not
another,
arguing for this. In some sense, this is not really like you're going to replace a layer of neurons with a much larger layer of neurons. You're going to replace a layer of neurons with two layers of neurons. One is much larger. Those are the dendritic segments, and the other one is.
But it's not a full layer. These guys are dedicated. They only have one connection.
Yeah, exactly.
It's not like these are fully connected to that.
Yeah.
So it's not a full layer. It's like it's got its own pool.
So you're gonna model it like this. You're gonna say, okay, here's my layer of neurons, which is like my classic artificial neural network layer of neurons, and now I'm gonna create this other layer of neurons, which is really big.
Dendritic units.
Yeah, and then these four are gonna go to here, and then these four are gonna go to here, and these four are gonna go to here, and there's nothing else going on. So you can do it that way, but it's kind of like saying you're doing it this way. I mean, it's just redrawing it differently.
Yeah, maybe the whole point is to read, the stuff that
But maybe it would be easier for machine learning people to understand because they are used to this idea that can be different classes of nodes. I'm just thinking whether it would be more helpful for talking to the machine learning community to think of this like, look, we're gonna introduce like a second class of unit here, right, which we call a dendritic unit. And then maybe they would understand it because then you don't have to talk about the biology of it. You can just talk about the fact that these units are a bit special in the sense that they have these converging inputs onto these other classes of nodes. I think it might be helpful.
Yeah, I mean, the point is that, especially for machine learning people, it has to be justified in terms of, performance or function, something else. So if we cannot say, okay, I developed this new neural model because it helps some properties or helps with the performance, then it's not gonna work. So
I mean you could do that, and you can have as comparison this flattened version. The flattened version is going to have many more parameters than this version. So there's an issue there, but you could certainly do that comparison.
What I'm thinking,
the logic, there's with continuous learning, you have to, I think about when you get this next class, how really the learning is going to happen. and it's a little tricky there.
What I was thinking of.
Oh, this is from Kevin's cheat sheet.
Yeah, exactly. What I was thinking of was just like these cheat sheets, right?
It's on Slack.
Where it's on Slack, right?
Kevin?
Yes.
Exactly. Where there's
He shared a bunch of cheat sheets. He made,
He didn't make them.
He didn't make them, he pointed us to.
This is a very famous one, neural network zoo. It's not a cheat sheet, it's a website.
Right,
Yeah, all
right.
these guys
So
are
it's-
neural networks.
it's one of the cheat sheets has like a zoo of classical neural networks in there. And so they show by different colors, right? Green are hidden units, and yellow are input units, and red are output units. And it's like
What's the blue one?
this like memory cell, recurrent cells, and memory cells, and different memory cells, matched input output cells, like So there's like different classes of nodes. And then they sort of like talk about these different architectures and sort of these terms, and they just put them together in like these nice color diagrams. And one way to think about this in machine learning context is exactly to say, well, there's one more category of node here, right? Just not a, which we call like a dendritic cell, and there's some special condition, it has to be layered with like these other, main cells. And then you could build an architecture that a machine learning person would understand without having to talk about dendrites and biological neurons.
You call them continuous learning cells, or you put them in a language that has value.
Right.
Continuous learning dendrite cells.
Non-catastrophic forgetting.
Yeah.
Catastrophic remembering.
Disappear performance cells.
It's an interesting idea. You propose it and make it so people can understand it.
Yeah.
Or
I'm just thinking, imagine a bridge. I mean,
Yeah,
I'm myself not so deep in the machine learning world that I can
I have
particularly understand.
found sort of
So,
an active, and this is mostly in the neuromorphic hardware world, but sort of an active distaste for dendrites. So you bring it up, they're
Right. I'm used to that. That is true. I've seen that too. There's a lot of people who would just like to please not be concerned with that. And so they, disregarding the evidence, they go like, look, let's, there's so many interesting questions we have outside of that. Let's pretend it isn't real.
It's really comforting to be in the point neuron world because there's so much existing stuff around there. People understand it, and there's math around it, and all it's very, very simple.
But then every time you add complexity, you have to justify it somehow in science or whatever.
Yeah.
The simpler it gets, the better it is. So
So
that's another thing,
Well, so we've shown the benefit of it,
Yeah,
but
exactly.
mostly it's for the prediction. Prediction is by its very nature is time-based. And so if you're going to build a predictive model of the world, then it's really valuable. If you're just going to do a classifier, well, then it's not so necessary.
But then again, machine learning people came up with these, recurrent connections that can somehow solve that too.
But I think Florian's point is that showing a picture like this, or maybe it's your sense of your idea, show a picture like this, and then just call them something, and we type a neuron, that we might get in a Trojan horse to get them to.
Right.
Oh, absolutely.
Here, they're going to go, these are really neurons of dendrites,
I tricked you.
It's not a Trojan horse for being screened, right? The whole point
Oh,
is Trojan
yeah,
horse.
tweet this.
Right. No longer a Trojan horse. We announce it now. They can still fall for it.
They're not paying attention.
Biology through the back door.
Yeah.
So I might jump into my topipic and then bring this back to continue.
Great, okay, why don't you go to the topic? We've probably got this for enough time.
So this is going to be the kind of jolting. I'm going to move us into a different topic, but then there's an interesting continual learning question on top of it. But my original purpose was this other thing, just to clarify a follow-up from Monday. So just, 30-second refresher. Like we had this kind of fairly complicated 4-layer network. Where it's like a big four-layer CNN. There's some details I'm leaving out here. And where what they were optimizing for is they want to be able to classify objects from this top layer. And even be able to classify novel objects without ever having to change this network. and the interesting observation was that by training a network on that purpose, they got something that where the top two layers like were their representations could be linear mapped onto representations between these. I mean, I'll just do like dotted lines. You could do linear regression from here to here to predict units firing. And now the one thing that I wasn't able to respond well to, or intelligently to, was that that this is self-evident that this would happen. The idea that if you can classify something linearly from here and from here, that almost implies that there must be a linear mapping between the two.
Yeah, I think that was the crux of the issue to me, is that true or not?
So I think over here I can describe that statement in a way that makes it obviously false. And
oh, that'd be good.
yeah, so first of all, like, I think part of the confusion came from, we were talking about both linear classifiers and linear regression, and I think the conversation got a little confused from that. So keep in mind that a linear classifier, so network output, this is either this or this, I call it X. A linear classifier comes from applying weights, you get a set of scores, but then you like remove most of the information from this. You do a maximum for it. So here I've shown like this unit has activity 4, this unit has activity 1, etc. But then you max it out, and
to pick the winning unit, which is the class.
And you might use softmax or some kind of SVM thing, but the point is you get something along these lines. And so to phrase it this way, like, consider two networks with outputs x1 and x2. You have two of these. If their classifications are always the same, does that imply that you can do this linear mapping? And so I've shown.
Yeah, I think with the max in there,
I think that's where the confusion came in.
Yeah.
And so it's really quite easy to just draw these example, like here.
No, I see what you're saying. The max is kind of messes that up then.
Yes.
Mm-hmm.
Yeah, but does the max absolutely necessary? But
That's what a classification is.
I know, but
The expectation is that different networks are gonna not output the same scores.
Hold on. So the weight is now this hyperplane weight, which is used to separate the two classes.
So here I've depicted two classes, class 1 and class 2. Class 1 is stars, class 2 is triangles.
Mm-hmm.
And I've labeled them A, B, C, and D, E, F.
if you didn't put the, I'm sorry, go ahead. If you didn't put the max step in, if you just went to the score back, would it?
Well, then it wouldn't be the case that that this is
I mean, I guess
It's kind
I
of a
was
strange
thinking,
question.
I was thinking when I was thinking about it, like,
Yeah.
I don't know the thing along these lines very well. But when I was imagining going up and back down again, I was imagining going from something like the, what you labeled network output X to some
Yeah.
score back in network output X2.
Just the linear combination.
Yeah.
And linear.
See, that was the
This
issue.
nonlinear step, this max step, then I would say, of course, then I can't do that.
So they didn't train the network so that its score function was something in particular. They trained the network so that this was always correct.
Yeah, but there's a one-to-one correspondence between, well.
No, there's
There's a many
ones.
yeah.
Very many.
But just, okay, all right, so I'm just
So
trying.
do you want to walk through this?
Yeah, so here I've just tried to show a picture, two different network outputs. One of them, this is a schematic picture. You could think of it as two output units, or you could think of it as a schematic picture for many units. And here is the weight matrix combined with weights and the bias, so the additive term causes this kind of decision boundary. And basically, yeah, I mean, what's really happening is here is like, I call it a decision boundary, but really it's a scoring function. It assigns scores, like you might actually have a triangle over here, but anyway, the point is, it's a scoring function. And now I've shown particular examples, 3 instances of class 2, 3 instances of class 1, and I've shown how 2 different networks might put them in different places. And I've intentionally drawn them in different orders, or where A, B, C, BAC, EDF, DEF, to show just like, it's pretty obvious you couldn't do a linear mapping from this to this. You couldn't multiply some matrix by this to move them to here because you can't change the order of things through linear mapping. And anyway, I think that this was where there was some confusion here. So it's at least from the perspective of linear algebra, linear mappings, matrix multiplication, whatever, it's not the case that this is self-evident.
I guess what I was thinking, I wasn't thinking about this max step at the end. I guess
It's sort of non-linearity really. That is
we were
the
talking
crux.
about, somehow we were all talking about these linear combinations,
Yeah.
linear stuff, saying, well, there's linear seems like to work, but now you do this other stuff. I can see why.
But you can certainly do, you can certainly rotate this whole space so that the classifications are still the same. It's just you're saying the order of these guys, if you're trying to predict this guy's response versus this, that's going to be, you can't do
Right.
that.
You're not going to be able to say that like, okay, this unit is at this activity level, this unit is at this activity level. I'm seeing A. From that information, I can predict these activity levels. That's not possible. That's not self-evidently possible.
Yeah,
Now-
like it might work, but there's no guarantee whatsoever.
Right. Now, I think maybe some of your intuition came from something that might be true. And in the paper kind of points this out, that this might be evidence that the statistics of the world are such that there really aren't very many bases where this is possible. There are maybe the statistics of the world are such that
That seems likely.
if you find this, like that, if you get this, you have converged toward like one perfect basis. There's only really there's only one small family of bases, bases that are mostly linearly mappable to each other.
Or even if there's multiple bases, maybe you'll just end up the same one, right?
Yeah.
I mean, there could be some weird ones.
So
Well, I wonder if it's something else could be true. It's suppose these are really high dimensional representations, here and here. And you have a relatively small number of patterns. It could be that even though technically this is true, in high dimensional spaces, you would be able to do that.
Because
it's not going to end up like this. Each pattern is just going to be in its own cluster somewhere, right? And so all you have to do is sort of map those clusters. I don't know if that's true or not again.
And I think my guess here is if an author on the paper were standing here right now, they would have the perfect answer to that question. They would say, we intentionally only sampled a small number of units, making sure we solved for that case. But I'm not going to be able to give a good answer to this.
So this was helpful. This was good.
And so the closing point on that part of this is there are two possibilities, maybe more, but two possibilities. One is that there really aren't very many of these bases where this is possible, and it's pretty cool that that deep networks are able to find it. Our brain finds it too, it seems. You could think maybe, like one way to map this, I'm not telling. Maybe, for example, the equivalent of the spatial pooler in temporal cortex in IT, that spatial pooler has a basis of sorts, and maybe it's actually quite similar to this basis. Maybe the right way to think of it. That's me trying right now to map it onto our world. If you're going to say something,
It's hard to say they're similar bases. I mean, what we're saying is that we can you can have a linear mapping from one to the other that's predictive.
Yes. So I think
but
if
the
this
dimensionalities could be still very different.
Fair. I guess
that's
the
why
way
you do like principal component, right? I mean, people have done that where they
But they didn't do that here. I mean, this could have a million dimensions. This could have 100 neurons.
all right.
They didn't control for that. Maybe they did. I don't know actually.
I don't have an answer to that either. So I guess when I say the same basis, I'm really thinking of bases living in these kind of families, or like this family of bases are kind of related to each other. You can kind of linearly map between them. This other family over here, And I'm saying that they're in the same thing.
And I think in high dimensional spaces, when things are sparse, that almost has to be the case. Again, that's, if you're going to be able to easily classify them, if you think about our SDRs, you have clusters of things that are going to be naturally far apart from one another. And then in that case, it'd be easy to disentangle them or whatever, map them.
Yeah, the other possibility I was going to bring up is possibility one, there aren't very many solutions to this where you can linearly separate them. Possibility two, there are a lot of them, but it just so happens that maybe convolutional neural networks learning rules are sufficiently similar to the brain's learning rules that they find similar ones. So why do they seem to find the same ones is an interesting question. And who knows, it might be a bug in the analysis, something like, there's still that possibility.
Yeah, but the analysis might be fine.
Yeah.
It might still, I'm still just wondering whether any high dimensional system that solves this problem would be able to map to these few hundred neurons they're testing.
Did they release that data? Like for the IT response?
That's a good question, because they do have a benchmark for comparing against neural data, but I don't know in detail of what data exactly they released, if it was this data.
Yeah, I guess the crux of the question is how constrained is this relative to the space of all possible models? And if this is really, really constrained and it happens to find this, then that's really cool.
Yeah.
But at least, do you know even if it was like high dimensional, would it all affect the fact that that mapping still held for images that it wasn't trained on? Because that was kind of strange. Like they find a linear regression, but that's only given the images that the CNN was trained on. And then they use that same linear regression for images that it wasn't trained on, right, to predict IT response. Is that correct?
So the linear regression from
CNN to IT.
No, when they were predicting neural responses, that was on. There's multiple levels of training here, so the conversation can get a little confused. For one thing, when they were doing backpropagation over here, they were using a totally different set of images, so a totally different set of image classes.
Yeah.
Later, when they were doing this testing, they were using a new set of image classes, and training, yes, a linear classifier. Sorry.
A linear regression.
Need to pause for a second. Yes, they were doing linear regression from units here to units here.
Was there a train set and a test set for that?
Yes. They didn't use the same images. They trained on some images and tested on others.
That's my curiosity. Like, it just seems like kind of interesting.
That's more of like this transfer learning question. Like, it's kind of interesting. It's cool that CNNs can do this kind of quote unquote transfer learning.
But I think maybe you're saying the fact that they were able to predict neural responses to novel images.
Yeah, exactly. Predicting neural responses to novel images.
Yeah, that's vital. If they hadn't done that, this paper wouldn't have been as impressive.
And then my question is, does that sort of you can sort of put this condition on, like, if they sort of restricted the complexity of the CNN, then maybe, like, let's say you just have this huge linear regression that's like very just complex, then, maybe you're sure that you'll be able to, do as much linear regression as you want and sort of get something. But then the fact that it sort of transfers over to new
novel images, yeah.
Yeah, it just seems as if like the dimensionality of the CNN wouldn't have made as much of a difference.
So I've mentioned that I'm going to bring us back to continual learning. Maybe I'll do that now briefly and see where it goes. So I just wanted to bring this image back into your mind of like, let's think of a deep network just for now as what it's doing is it's trying to make its top layer linearly classifiable. And if you think in those terms, now the question of continual learning becomes kind of a two-part question of, like, suppose you see batch 1 of images, then you see batch 2 of images, etc. You can kind of decompose this into two parts. It's like you want the basis to continue keeping everything linearly separable for the old images.
Right.
And you probably have to update your classifiers for the old classes. And I don't know, that just provides a point of view that it really matches. I know, like, in what Vincenzo presented had like the feature layers and then at the other one. So it's like, it goes in line with that. I guess this is kind of a mental model of what deep networks are doing. When we talk about our compartmentalized dendrites, that's like adding memory to the system. But this is more of like a generalization system. This is more like a memory system. And it's not just gonna match. It's worth experimenting with, but our work's not cut out for us. It's not just gonna magically, there's some cleverness is needed still, some insight. But in some ways the systems are different.
Is that true? I mean, if you think about this version of the drawing, I mean, it's just going to do back propagation throughout the whole thing.
Sure. Fair.
So it's not so much a memory system anymore.
Okay. You know, this is a good
In some
point.
sense, it's gonna be very similar to what we have in sparsity method, right? If
Yeah.
you have the same nonlinearity in both places.
Yeah, with stopping, right? I mean, the idea being that it doesn't go all the way through the network again. You say preserve much of the lower level basis, right? And what you mostly are going to change is just the readout layer.
Well, you'll change some sparse subset of the
Right.
network as you back propagate. Most of it will be
No,
stopped.
that's why I asked if sparsity may be enough to with sparse connection like that. No, I didn't justify that, somehow you can maybe get rid of the active dendrites or more complex neural model, you move towards that. And then in that you can sparsify a lot of the connections and the activations are very sparse, is entangled representation.
That's right.
And you can somehow have this nice property of, you don't have to back propagate everything. The gradient stops at very different points. You can preserve a lot of these weights.
Yeah.
Produce knowledge, that's cool, but.
I mean, that would apply here too, essentially.
Yeah, exactly. So without doing anything much more than sparsity, okay, but then I was trying to think about.
I think it's primarily a efficiency issue.
Yeah, and then, but maybe still we need, still to preserve the weights at the same time, a bit more, like through consolidations, freezing, or something like that. As sometimes maybe a neuron can far to detecting a feature that is useful for recognizing an old task or an old class as well as a new class. And then what happens is that, for example, in upper layers, let's say also in classification, to make it more simple, if you in the back propagation, if you look just at the new class, you're gonna potentiate the connections, the weight towards that neuron.
Look at you using neuroscience.
Well, and you're gonna decrease the weight value of the weights connecting to the previous neuron or class, right? So that, for example, is an example in which you're still having this property of stop back propagation gradients is not going to be enough if
That's right.
the neurons, that particular neuron fires as well.
Yeah,
It
so
happens
that's
to fire as well.
well. I mean, this neuron has to fire, and these guys have to fire.
Yeah,
too. So you would still have that problem to some extent, but it'll be less.
Yeah, of course.
It'll be less, but maybe you can now use this elastic weight consolidation
Yeah,
stuff.
exactly.
Yeah, and it might be much easier because it has to solve a much simpler version of that.
So let's say that these neurons can activate, and so for example, this is useful to predict this new class, as well to this previous class. So it happens that this is going to be increased, and this one is going to be decreased if we don't see if this gets activated for some reason. Maybe this feature is very important to that particular neuron.
So this is going to be activated, but it's not useful for the new training data that we have. And so in the end, this is going to get penalized or is much more increased, and so it's going to mess up somehow, even though we have sparsity, right?
Yeah,
So,
yeah.
In this case.
Yeah, so sparsity will reduce the chance of that, but it will still happen. And maybe with elastic weight consolidation,
Or something like that,
you
we
can
can-
solve it. The other thing that we do is, our negative error in the HTM is often, in this case of where you have a misprediction, we think about in temporal memory, the negative error is much, much smaller than the positive amounts that we add. So that the decrease, so partly for this reason, because you can make, in the case of temporal memory, you can make a lot of predictions, only one of them will actually happen, doesn't mean the others were wrong. Right, so maybe the translation here, and I have no idea if this will work, is in the case where it correctly predicts something, the increase in the where.
Different learning rates.
Different learning rate for different, depending on whether it was correctly done or not.
But that is
I don't know
also
if that
because
also-
you are right much more seldomly than you are wrong.
Correct, yeah.
So that's why it's fine to do little depotentiation.
Yeah.
Because you cannot get a lot of little depotentiations.
That's right, yeah.
Right.
And it depends, in this case, how many classes you have. If you have 100 classes, it's,
Right.
I don't know if that logic really applies here or not, but that's something that came to mind.
I want to try one more time to articulate, because I've done a poor job so far. I guess what feels strange to me with this, okay, here, I'll try to say back what we're trying to do with these separate dendrites. We are making it so that subsequent training data doesn't stomp all over the weights, doesn't stomp all over old weights. We want them to be kind of guarded from later training data. But there's this conflicting interest that we want the network to always be searching for this really good basis. And we want it to continue using future data to change its basis. And those two are at odds with each other. Those two things seem at odds, preserving weights versus having your basis get better and better as you observe ImageNet. They seem, there's a contradiction there. There's something, there's a dissonance.
And maybe one thing I could say, the temporal memory side is on one extreme where we're literally memorizing everything.
Yeah.
And pure dense backprop is at another extreme where you don't care at all about the previous stuff. Every learning step is trashing everything. And maybe there's a sweet spot there where you still have some of that problem of trashing all stuff, but you really reduce it, but you allow the system to create more generalizable bases. It doesn't mean you have to be always at these two endpoints.
Yeah.
Yeah, absolutely.
The question is that just a trade-off, or is there a smart policy, right, that can get most of both? I mean, I wouldn't know what that looks like.
Well, the answer is yes, because we can do it. We know humans do it.
Right.
So there is one.
Right.
We just have to find it.
Maybe you should study the brain and get some insights.
That's a no-brainer. Okay, I think we're.
No,
Is this helpful at all, or?
yeah, absolutely. Yeah.
It was a nice and far-ranging discussion, I think.
Yeah. So that was only one question, was it?
Or two. One, two questions, and a revisiting of a complication from last time.
Thanks, guys.
Thank you.
Thanks. Are we stopped?
Uh,
That's that over the line.